Good afternoon, everyone. This will be our third session and the final session on deflection of statically determinate structures. So far, we have looked at the elastic beam theory, and we have looked at 3 or 4 methods to calculate the deflection of beams under mostly due to moment action. And those methods were double integration method, the Colles method, moment area theorems, and conjugate beam method. Today, we will study the energy methods of calculating deflection of structures. And as I mentioned, that energy methods can account for deflections due to bending as well as due to other actions like axial forces and shear forces. I'll be mainly covering 2 methods of, that is the virtual work method and the Castigliano's theorem. Both these methods are pretty much similar. There is a slight difference. We'll see that when we discuss the methods in detail. And in today's talk, what I'll do is I will first deal with trusses. I will cover the virtual work method for trusses as well as the Castigliano's theorem for trusses. Then we'll take a small break where I'll open the discussion for any questions that you might have, and maybe then take a small 5-minute break like we have done in the previous 2 sessions. And after we come back, we'll talk about again the virtual work method and Castigliano's theorem for beams and frames. So to start with the virtual work method, we'll just go through a brief theory about these methods that we'll be using. So the methods that we covered in the second session were the moment area theorems and conjugate beam method. Both these methods are basically semi-graphical methods where you need to have some idea about the deflected shape, and then you can use these methods to calculate the exact deflection at a given point. So these semi-graphical methods are effective for finding slopes and deflections in beams subjected to simple loadings, and mostly due to the bending action of these beams. And today the energy methods that we'll cover will be used for calculating slopes and deflections of beams under complicated loadings, and also in structures such as trusses or frames. These trusses deform mostly due to the axial deformation of the truss members. The frames, they deform due to axial deformation, bending deformation, as well as shear deformation of the frame members. So if you want to use the semi-graphical methods for calculating the deformation of trusses, it will not be very useful because semi-graphical methods are based on the elastic beam theory, which is taking into account the bending deformations only. It can take into account the deformation of frames, but you will see that the energy methods that we are going to learn today are more effective for calculating the deformations of frames because it takes into account the bending deformations and in addition the axial load and shear deformations. Now, most energy methods that are used for calculating deflections are based on the principle of conservation of energy, which means that the work done by all the external forces acting on a structure is transformed into internal work or strain energy. So if UE represents the external work of all the forces acting on the structure, and UI represents the internal strain energy due to the external loads, then the energy methods are based on the principle of conservation of energy. In other words, UE is equal to UI. Now, how does the strain energy develop in the structure when you apply loads? Basically, what happens is when you apply loads on a structure, all the components of the structure, they undergo deformation internally, and the strain energy is internally developed in the structure due to the deformation of the components of the structures. Now, because of this strain energy, the structure has the ability to come back to its original shape once the external loads are removed. So we'll now see how we can correlate this external work with the internal strain energy in a structure under some given loads, and thus use that method to calculate the deformation of the structure at any particular point under some given loads. To start with, what we'll do is we'll just quickly go over some theory about work done and internal energy. So first thing is that I would like to talk about is a straight rod or a bar which is subjected to an axial load F here, and because of which it undergoes a deformation delta. So at any instance, the energy inside the external work that is done by that force Fx in order to undergo a displacement dx is given by this equation du, where du is the small amount of work done in order to move that load in order to move that load by a distance dx along the axial direction of the member. So the small work done is due is equal to fx dx. Now if the rod undergoes a total deformation of delta under this load F, then at any value or at any deformation x between 0 to delta, the force that has to be applied is proportional to the displacement or deformation of the rod. So if the final deformation is delta and the final force is P, then for a deformation x, the force that has to be applied is given by P by delta over x. So it is directly proportional to the deformation of the rod. So for a deformation of x, the load that has to be applied is x over delta into P, where P is the load under which it undergoes a final deformation of delta. Now work done by the force Fx undergoing a displacement delta x in the same direction as the direction of the force Fx is given by Fx dx that we saw. Now that is for the small displacement. Now if you have to get the work done for the entire displacement from 0 to delta, what you do is you integrate it from 0 to delta with respect to x. Now here fx can be replaced by this expression, which is P by delta into x. Now here P and delta are constant. This is the final load and delta is the final deformation. So if you put that here, and the x also comes here, and you do the integration from 0 to 0 to delta with respect to x, then you will see that the external work done is given by half P times delta. So in other words, if you plot the deformation of the bar with respect to the force, you will see that the force is increasing from 0 to a final value of P for a final deformation of delta. So this curve basically represents the straight line represents the load deformation relationship of the bar, and the external work that has been done by this load P to deform this bar by an amount delta is given by the area of this triangle, which is half P times delta. Now what we'll do now is, in order to understand the concept of virtual work, we'll see what happens if we take that same rod on which a load P has been applied to get a deformation delta, and we'll apply an additional load of F dash, due to which it undergoes an additional amount of deformation delta dash. So the final deformation of the bar now is delta plus delta dash, and the total load acting on the bar is P plus F dash. So if the rod is subjected to a force P and having an elongation delta is subjected to an additional force F dash under which it undergoes an additional deformation delta dash, then the total work done is now half P plus F into delta plus delta dash. In other words, if you again plot the load deformation load versus deformation curve of this rod, you see that from P it has now gone up to P plus F dash, and the deformation has gone from delta to delta dash. So the total work done on that by the force is by the area, is given by the area of this entire triangle, which is half P plus F dash into delta plus delta dash. Now out of this, the work that is done by the additional force F dash is given by half F dash into delta dash. That is the area of this top portion of that triangle. Whereas the work done by the force P, which was already applied to get a deformation delta, is given by P times delta dash. That is the additional deformation that occurs after you apply the additional load. So the work done by the load which was already there due to the additional deformation is given by P times delta dash. That is the area of this shaded rectangular portion under the curve. So this triangular portion represents the work done by the additional load F dash, and the work done by the already existing load P to undergo the additional deformation is P times delta dash, so that half term does not come here for the load which is already existing. So this concept will be used when we study the method of virtual work in details. Now instead of load, if you have a moment in the acting on a member, and the work done by the moment undergoing a rotation theta in the same direction as the direction of the moment is given by m times d theta, where d theta is a small rotation in the direction of the moment, and then you integrate that from 0 to theta. Theta is the final deformation that is, or the final rotation that is undergone by the system on which the moment is applied. Now, again, if you want to know the work done by a gradually applied moment on a linearly elastic structure undergoing a total deformation, a total rotation theta, which is given by half m into theta, just like the work done for linear expansion is half p into delta. So for under a moment, the external work done is half into m into theta, where m is the applied moment and theta is the total rotation that the system undergoes due to the applied moment m. Now similarly, in this case, if you have a system which has been subjected to a moment m and it has undergone a rotation theta dash, if that system or structure is subjected to an additional moment of amount m dash due to which it undergoes an additional rotation theta dash, then the work done by the previously applied moment to undergo that additional deformation of theta dash will be given by, instead of half m and theta dash, it will be m into theta dash. So again, this concept will also be used in the principle of virtual work when we have to calculate rotation of structures. So the rotation that takes place, the additional rotation that takes place, the work done due to that additional rotation by the existing load is given by m into theta dash, where m is the moment which has already been applied and theta dash is the additional rotation that undergoes due to an additional moment which is applied on top of the previously applied moment m. Now coming to the strain energy due to the axial loads. So if you have a bar or a rod which is subjected to an axial load n, it has a length L, cross-sectional area A, and due to this load n, it undergoes a total deformation delta. Then the stress in the rod, we all know, is given by the term n over A, where n is the axial load applied and A is the cross-sectional area. The strain in the rod is given by delta, where delta is the total deformation that it undergoes under the load n, and over L, where L is the original length of the rod. Now, if the material of the rod is linearly elastic, that is, it follows Hooke's law, then the axial stresses and strains may be related by the relation sigma is equal to E times epsilon. That sigma is the normal stress, which we have expressed here, epsilon is the normal strain, and E is the modulus of elasticity. Now, if you substitute the expression of sigma from this top expression into the second equation that you see, and you substitute the expression for strain into this part, then you will get the deformation delta can be written as n into L over AE. Now the external work done by this load n in order to deform this rod by an amount delta, we saw in the previous slide that it is external work. Now this rod was initially not applied to any loads or not subjected to any load. Load n was gradually applied to it, due to which it undergoes a deformation delta. So the external work that is done by this load n is half into n times delta. So instead of delta, if you replace the delta by this term NL over E, the internal strain energy that will be developed in the rod is equal to n square L over 2AE. This is half into n into NL over AE. So that is how, if we equate the external work to the internal strain energy, the internal strain energy can be obtained like this, n square L over AE. Now this is for a rod which undergoes a deformation of amount delta. It was initially undeformed, so the load n was gradually applied on it. So the internal strain energy of that rod is given by this expression, n square L over 2AE. Now if you have objected to some external load because of which it will have bending moment at various sections, and if you consider a small section of the beam which undergoes a rotation d theta and has a length dx, a distance x from the left end of the beam, then the moment due to the external load is given by mx at the distance x. So if you recall, this relationship was already obtained from the elastic theory of beam, where d theta dx is equal to m over ei. So we are again writing that relationship. So d theta is equal to mx over ei dx. So d theta is the small rotation of that element of length dx subjected to a moment m. Ei is the flexural rigidity of that section. Now, if you want to calculate the internal strain energy due to this bending action, the internal strain energy due to the small rotation d theta is given by half mx into d theta. Now again, you can replace d theta by mx over ei into dx here, so you will get mx whole square dx over 2ei. So that is the expression for the small increase in internal strain energy due to the bending deformation of this section of the beam. If you want to calculate the strain energy developed over the entire length, all you do is you integrate both sides of this equation. So you will integrate this over the entire length of the beam. So that will be integration mx whole squared by 2ei dx. So if you do this, you will be basically getting the internal strain energy in a beam due to the bending action. So in the previous slide, we saw the internal strain energy due to axial load, and in this slide, we see the internal strain energy due to the bending action in a beam. So now we'll see how we can use this principle of conservation of energy to calculate the deformation of this cantilever beam. So what happens here is we have a cantilever beam which is subjected to a load P at the free end. The length of the beam is L. So if the beam undergoes a deflection delta under this load P, the external work that is done by this load P is half into P times delta. Now this is assuming that it was not loaded, and this load P has been gradually applied from a value of 0 to P, due to which it has undergone a deflection in the direction of the load from 0 to delta. Now if you want to find the bending moment at any distance x from the right end, in this case, the bending moment is given by minus P into x. So if you want to calculate the strain energy, this is the formula that we saw in the previous slide. So it is given by integration 0 to L mx square by 2ei dx. Now here your mx is minus px, so you put that here and you integrate it. So if you do the integration, you will be getting p square L by 6ei. So this is the internal strain energy, this is the external work done by the load. If you equate these two, you will see that the delta, which is the deformation, the deflection of the beam under the load, can be obtained as PL cubed by 3ei. So this is the deflection of a free end of a cantilever subjected to a concentrated load, and you see in this slide how we can obtain this deflection by equating the external work done by the load to the internal strain energy of the beam. Now if you can, this is one of the simplest way of calculating the deflection of beams using the energy method. There are some limitations. If you try to do it this way, you can calculate the deflection only under a single load at one time, and it will give you the deflection at the load itself. It will not give you the deflection at any other point of the beam. So this method can be used. That is, so far we have not introduced any virtual load into the system. It was an applied load that we used, and using the method of conservation of energy, we have seen how we can calculate the deflection under the load. And again, this method can only be limited to calculation of load under the load itself and under a single load at a time. If there are multiple loads, if you want the deflection at some other point other than the load point, then this method will not be useful. So in order to overcome that limitation, the principle of virtual work has been introduced, which is having a similar concept as the principle of conservation of energy, but there is a virtual work or a hypothetical load that is being applied, and a work is calculated due to that load is considered. So let us look at this system, which is subjected to three different external loads, P1, P2 and P3. Now if a deformation is required of this system at a point A, which is independent of the point of applications of the load. So it is not any of the 3 points where the load is applied, it is some other point. So now if we have to calculate the deformation at a certain direction of the system under these given loads, then what we do is we introduce a virtual load like this, which is shown here. So if we have to calculate the deformation of this joint, of this point of that system in this direction that is shown here, what we do is at that point we applied a virtual load P dash whose value is equal to unity in the direction in which the displacement is required. So that is the first step. We apply a virtual load P dash equal to 1 at a point in the direction of delta. So now what we are trying to calculate is the deflection in this along this direction at this point due to these external loads that are being applied on that system. The next thing that we do is calculate the internal virtual load in all elements of that system or body due to the virtual load. So we apply a virtual load of unity and we calculate the internal loads in all the elements of that system due to this applied load. The next step is we apply the actual loads. So apply the actual loads P1, P2 and P3. Now the virtual load is not there, and again we calculate the internal deformation in all the elements of that system due to the real loads. So now due to the real load it has undergone some deformation. So the virtual load which is already there will also undergo a deformation which is delta due to the application of these three external loads. So that is why, so the work done by the virtual load due to the deformation that is caused by the external loads at point A in this direction is delta. So the virtual work done is 1 times delta. Now what is the virtual internal energy? We have already calculated the internal virtual loads due to this unit virtual load in all the elements of the body, and also due to the applied external loads we have calculated the internal deformations of all the elements of the body. So the virtual load times the internal deformations due to the applied load will give you the internal virtual strain energy. So now if you equate the external work of the virtual load to the internal virtual strain energy developed in all the elements due to the internal deformations under the real loads, then you will be getting this relationship 1 dot delta equal to summation of U dl, where U is the virtual load in individual elements due to the externally applied virtual load of unity, and delta L is the actual deformation of all the elements due to the externally applied loads P1, P2 and P3. So if you equate this load is unity, so basically if you calculate the right hand side, that is the value of the deformation delta. Now if you have to calculate rotation at that point, the same thing would have been done, only difference would have been instead of applying a load, we would have applied a unit moment, and so the unit moment times the actual rotation at that point due to the applied load would have been equal to the, again, the internal strain energy, virtual strain energy due to the internal virtual loads and the actual deformations of the elements. So we add the product of the internal virtual load and the deformation due to the external load of all the elements, and that will give us the rotation of that element at that point A. So this is for a general system. So from a general system, we'll now move on to a truss. So if we have to find a deformation at this point B in a truss in the downward direction, the actual loads on the truss are shown on this figure on the right hand side. This is P1 and P2, and you want to calculate the deformation in the downward direction at this point B. Now to use this method of virtual work, what we do is we apply a virtual load of magnitude unity at this point B in the downward direction. Under this virtual load, we calculate the member forces in all the truss members individually. The next thing that we do is we apply the externally applied loads, in this case P1 and P2. So because of these externally applied loads, we again calculate the axial forces in individual truss members. So whatever is the individual axial force in the truss member, because of that the truss member will undergo a deformation of NL by AE, which we saw in a couple of slides back. If a rod is subjected to an axial load N, it has a length L, cross-sectional area A and modulus of elasticity E, then the deformation of that rod under the load N is equal to NL by AE. So the virtual member force under this externally applied unit virtual load is N. So that times the deformation of individual members due to the external applied load is small n times N into L over AE. So if you add all the internal strain energy, the virtual internal strain energy in all the members, you will be getting the deformation of the truss at this joint B where that unit virtual load is applied. Now if you get a positive value from this terms that are calculated shown on the right hand side, then that means the deflection of the truss is in the direction of the virtual load. If you get a negative value, that means it is in the opposite direction in which the virtual load has been assumed. So to get a better idea about this method of virtual work for trusses, we'll now look at an example where we have this simple truss ABC, which is having a pin joint at A and a roller joint at B. It is subjected to a lateral load of 4 kilonewtons in the horizontal direction, and they want you to calculate the vertical displacement of joint C, that is the downward or upward displacement of joint C due to this applied load. The cross-sectional area of each member of the truss is given as 400 millimeters square, and the modulus of elasticity of each member is given as 200 GPa. Now, since we have been asked to calculate the vertical deflection of this joint C, if you want to use the virtual work method, what we have to do is apply a virtual load of amount unity of magnitude unity in the vertical direction at joint C. So that is what we will do to solve this problem using the method of virtual work. So we have two cases. One is the truss under the external load of 4 kilonewtons, and the other one is the truss under a virtual load of 1 kilonewton in the downward direction at C. So under both these cases, what we have to do is we have to calculate the member forces in each of these three truss members. So those are shown on this slide. So you can see that for a lateral load of 4 kilonewtons, the reactions here would be 4 kilonewtons in the opposite direction, a downward reaction of 1.5 kilonewtons, and an upward reaction of 1.5 kilonewtons at this point. And the member forces are 2 kilonewtons, again 2.5 kilonewtons minus 2.5 kilonewtons. This minus term indicates this member would be in compression, and since these two are positive, that means this would be in tension. So member forces in the three truss members due to this apply 4 kilonewtons acting to the right. Now again, if we consider the member forces in the individual truss members due to this virtual load of 1 kilonewton acting in the downward direction at C, you will see that the reactions 0.5 kilonewtons each at each of the supports, and the member forces would be 0.667 kilonewtons in this member AB and minus 0.833 kilonewtons in each of these members AC and AB. So now what we can do is we have to calculate the term NL over AE. So small n here is the member force due to the virtual load, and capital N here is the member force in each of the truss members due to the applied loads. So all these are representing capital N in each of the members, and these numbers are the small n. So we have put them down in a table. Now there is also the terms A and E in the denominator, small n into capital N into L over AE. Now since those A and E for all these three members are constant, we do not take them into account in the table. We'll do it finally. So what we have done in this table is we have written the member force due to the virtual load in one column. We have written the member forces due to the applied loads in one column. We have written the lengths of the individual truss members here in this column. And in the last column, we have multiplied these three, small n, capital N into L. We multiply these three and we then add them up. Now notice that if there is a negative sign due to this multiplication, we have to consider them. We cannot ignore this negative sign when we are adding them up. So basically minus 10.4125 and plus 10.4125, they will cancel. So if you add all these three up, you are left with 10.672. So this is a very important thing to remember when you are using this method. The negative signs should not be ignored. So this is the summation of small n into L over into N into L. Now that has to be divided by AE for all the members. So A was given as 400 millimeters square, E was given as 200 GPa, which is 200 into 10 to the power 3 Newton per millimeter square. So if you put that, so 1 times the deformation of the truss at C in the downward direction due to the external load is equal to summation of NNL over AE. Now summation of NNL from the previous slide came out to be 10.672. If you go again, you can see that is where we are getting that 10.672 from. So that divided by 400 and 200 times 10 to the power 3 is the value of E. So that comes out to be 0.1334 millimeters. So that is the vertical deflection of the truss at this point C. Now since it is positive, so that means the direction of that deflection would be in the direction of the virtual load that has been used. So here we have used the virtual load of 1 kilonewton in the downward direction. So that means the vertical deflection of that point of that joint C would be also in the downward direction. So that was a simple example to demonstrate the method of virtual work for calculating the deflection of trusses. Now this method of virtual work can be applied to calculate deformations or deflections in trusses or in truss joints due to other factors such as temperature changes and fabrication errors or camber. So for considering temperature changes, if you have a truss which is subjected to external loads as well as there are temperature changes in some of the members. So any temperature change in any of the member will cause either an expansion or a contraction of that member. So if you remember the formula for calculating the temperature, the deformation or the change in length of a member subjected to a temperature change delta T, it is given by alpha times delta T times L, where alpha is the coefficient of thermal expansion and delta T is the change in temperature, L is the length of that member. So that is the changed or deformation of the member due to the thermal change. So if you want to use the method of virtual work to calculate the deflection of this point B due to a change in temperature of any member of amount delta T, then what you do is you calculate the deformation of that member due to the temperature change and you multiply it with the virtual load in that member due to the virtual externally applied virtual load of magnitude unity at the joint where the deflection has to be calculated. So again you apply this unit load, you calculate member forces, the member where the temperature change is occurring only. So if you calculate, if this was the member which was undergoing the temperature change, then you find the load due to load in that member due to this applied virtual load, that would be N, and that multiplied by alpha into delta T into L would give you the deformation of this or the displacement of this joint due to the temperature change in this member. Now again, this method can be used for calculating the joint deflections due to fabrication errors. So if a truss is given and it was found that one of the truss members was fabricated with an error, that means it was either a little bit longer or a little bit shorter than what was the given length of the member. In those cases also, this method of virtual work can be used to calculate the displacement of that truss joint because of the fabrication error. So the displacement of a selected truss joint resulting from the change in length of a truss member by delta L due to a fabrication error or due to counter camber measures can be obtained as 1 into delta L, where delta L is the joint deflection due to the fabrication error, and that here the change in length is already given, that is the fabrication error, to delta L. So that multiplied by the load or the member force in that member due to the applied virtual load. So here it is, again, if the joint deflection at this joint B is required due to a fabrication error in this member and the fabrication error is delta L, what we do is we apply the unit virtual load, calculate the member force in this due to the applied the unit virtual load, and so that is N, so that times delta L would give you the deflection of this joint. Actually, I already got some questions. I'll just finish the method of virtual work and Castigliano's theorem for trusses, and then I will start taking all the questions. So then I'll also consider this question which has already been asked. So again, we have another example where you have that. Now instead of that external load, what is we are saying is this member AB is built 5 meters too short. That is, whatever the length of this member is actually 8, but it has been found that the member has been 5 millimeters less than 8 meters. So that is, it is 7.995 meters. Now because of this, they are asking you to calculate the vertical displacement of this joint C. Now in order to do that, once again we apply the unit virtual load and we calculate the member forces in this member where that fabrication error has occurred. So that is 0.667. So the deflection of this joint C in the vertical direction is 0.667, that is the member force in that member due to the virtual load, times the fabrication error. In this case it is 5 mm too short. Now this 0.667 is tension, and this is short means it is the change in length is due to compressive action. So it is -5. So it comes out minus 3.335. Now here it is minus, the virtual load was assumed to be in the downward direction. Now since the answer came out to be negative, that means the vertical displacement of this joint due to the fabrication error in this member will be in the upward direction, and the magnitude of that displacement or deformation would be 3.335 millimeters. So that was the virtual work method for trusses. Now we will talk about Castigliano's theorem for trusses. It is, as I mentioned, it is very much similar to the virtual work, but with some slight changes and some slightly more advantageous, or it is slightly more quicker in some cases. So that is why I decided to also talk about this method. And this method states the displacement of a selected truss joint is equal to the first partial derivative of the strain energy of the truss with respect to a force acting at the truss joint in the direction of the displacement. So now if you want to use this method, there are certain steps to be followed. So if you have a truss and you are told to calculate the deflection or the displacement at a particular joint, what you do first is you apply a load P in addition to the given external loads on that truss. The load P should be applied at the joint at which displacement is to be calculated. The load P should be applied in the direction of the displacement which is to be calculated. So just like the virtual work method where you are applying a virtual load at the joint and the direction of the displacement, you are applying a load P instead of a unit virtual load. Then what you do is you calculate the member forces in all the truss members due to the external load as well as the load P that is you have applied. So here you don't have to calculate the member forces separately due to the load P and the external loads. You calculate the member forces combined due to the external loads as well as due to the load P. Now here the strain energy in all the truss members due to the member forces is given by n square Li over 2Ae. So if there are n number of members, it will be I is equal to 1 to n. So internal strain energy is given by n square L by 2Ae. So this n is the member force due to the external loads as well as the load P that we are applying at the joint where the displacement has to be calculated. Now if you want, so this term n for individual truss member would be a function of this external load P that you have applied. Then what you do is you take the partial derivative of this strain energy with respect to P. So if you do that, all these other terms L, A and E, they are independent of P. So the partial derivative would be 2n del P. So that 2 will cancel out in the numerator and denominator, and you will be left with summation of n, where n is the load due to external loads as well as P, times del n del P times L over EI for individual members, and you take the summation. Now when you put this term n here, remember the n is in terms of external loads as well as P. So n will be a function of P. So when you want to calculate deformation, then what you do is you apply the actual condition, that is actually there is no load. So you say P is equal to 0. So then you will be able to get the the estimate of the deflection at the required joint. Again, in order to explain this more clearly, we'll take an example very shortly. But before that, I just wanted to mention some key points. So as I said, the displacement of a selected truss joint is equal to the first partial derivative of the strain energy of the truss with respect to a force acting at the truss joint in the direction of the displacement. And we saw that this is the final formula for calculating the displacement, where N is the member force due to external loads as well as P. This is the first partial derivative of member with respect to P in each of the truss members. LA over AE. L over AE is the constant for each truss member, so it is not dependent on P. So we can, if you take the partial derivative, this won't be affected. And finally, this has to be calculated at P is equal to 0. Now, when I solve one of the assignment problems, or when I discuss one of the assignment problems during the later part of this session, you will see that if you want to calculate the deformation under a given load, that is if a load is applied, let's say in the vertical direction in the truss, that is an actually applied load, and you want to calculate the deformation also in the direction of that load at that same joint where that load is applied, then in that case what you do is you can still use this method, but instead of putting P is equal to 0, you put P is equal to the value of the external applied load. I'll talk about this in a little more detail when I discuss the assignment problems at the end of the session. So before I go into an example, I just wanted to mention some key points about this Castigliano's theorem. First of all, this method is applicable to trusses having constant temperature, unyielding supports, and linearly elastic material response. So this cannot be used for calculating deformations due to temperature changes like we did for the virtual work method or for support displacements. This method is similar to the virtual work method with the exception of N being replaced by dN by dP. So in the virtual work method, it was capital N into small n into L over AEP. So instead of that small n, we have del N over del P. And also in this method, you should remember to retain the algebraic signs for the corresponding values of N and del N and del P when you are substituting these terms in this equation. The above value of delta calculated using the value of delta calculated using the above formula is positive, the displacement of the truss joint is in the direction of the load P. If the value of delta calculated using the formula is negative, then the displacement of the truss joint is in the opposite direction in which the load P has been assumed. So what we'll do is we'll again go back to the truss that we solved using the virtual work method, and now we'll see how we can find vertical displacement of this joint C under this external load using Castigliano's theorem. All other conditions that were applicable to the truss are identical here. So the area of each member is 400 and the modulus of elasticity of each of the members is 200 GPa. So now if you want to use the Castigliano's theorem, so now we don't have to apply the external loads and the load P separately. We'll take only we'll take the truss just once, we'll apply that external load as well as that load P. And now this is what I wanted to show you. The support reaction here would be P by 2 minus 1.5, and here it will be P by 2 plus 1.5. And also the member forces in the three members would also be functions of P. So it is minus 0.833 P plus 2.5 minus 0.833 P minus 2.5 plus 0.667 P plus 2. So these are the member forces due to the external load and that load P. So now this your N is the actual member forces due to the external loads and the P. So all of them are functions of P. So if you take del N del P, you will get 0.667 minus 0.883 minus 0.883. And here you take N at P equal to 0. So put P equal to 0, you will get 2, 2.5 and minus 2.5. Now if you go back to the solution of this problem using the virtual work method, you see these two columns, these are identical. So N was 2, 2.5 and minus 2.5. And here the small n was 0.667 minus 0.833 minus 0.833. So here also those two columns are identical, only a difference is you are having a different heading here. And here we are applying the load P and the external loads simultaneously on the truss. And these are the lengths of the member which are different for each of these truss members. Again, you multiply the three columns, del N del P, N, L, you get 10.662. Again, minus 10.412 for AC and 10.4125 for BC. Again, don't neglect the signs, add them up, get 10.672, and then again you divide it by AE, you get the vertical deflection at joint C. So that was a quick demonstration of calculation of vertical deflection of a truss joint using Castigliano's theorem. So that basically concludes the discussion on energy method, that is the virtual work method and Castigliano's theorem for trusses. So as I said, we'll now take questions on these two topics. And if you have any questions, you can either chat it or raise your hand, use the raise your hand option, and I'll be glad to take those questions. So I already had a question. So is saying, in the case of calculation of virtual work, why we don't get gradual application of load, or in case of virtual work, energy is force displacement, and in so this is the concept of existing load that I talked about when I was discussing the theory of virtual work. Yeah, so what we did is we first applied the virtual work. So in this case, the virtual work is P, and the external load represents FF dash. So the work done due to the virtual work, when you apply the external load and it undergoes this additional deformation delta dash, is P times delta dash, that is represented by this shaded area. So it is gradually applied load, but the virtual work is already existing, as in the case of this load P here. So because of that, the work done due to the virtual load is P times delta and not half P times delta. The total work is again half P plus F prime into delta plus delta prime. So because the virtual work is first applied and then the external load is applied, so the external work of the virtual load to undergo the additional deformation due to the external loads is P times delta, that is shown here. So if you have any other questions, okay, since we are not getting any questions, what I'll do is I'll take a 5-minute break, and in the meantime, if you come up with any questions, you can text them or chat, type it in using the chat option, and when I come back before I start the virtual work method and Castigliano's theorem for beams and frames, I will take up those questions. Okay, thank you. Okay, I got some questions during the break. First question was, what is unyielding supports? Unyielding supports are supports like pinch supports, roller supports, which do not have any displacements. Now, there might be structures where the supports might undergo some settlement or some displacement, even though it is providing restraint. So these are called yielding supports. So unyielding support means the regular supports that we encounter in structures where they do not allow any deformations or deflection at those support points. So that is the answer to your question, what is unyielding supports. Please give examples for linear elastic material properties. When I say linear elastic material properties, what I basically meant is the materials have not undergone the yielding. In other words, the E value remains constant no matter what is the load. So if the load is within the yield load, the material is said to be having linear elastic material properties. The value of E, that is the modulus of elasticity, remains constant. So that is an example of a linear elastic material property. In other words, the load on that material has not reached the yield limit. So that is a case where it will be having linear elastic material property. If we convert a uniformly distributed load to a point load, then whether we can find the deflection under that point load by using Castigliano's theorem. If you have a structure with a uniformly distributed load and you want to calculate now if you are talking about trusses, you must remember that in trusses the loads are applied at the joint. But if you are talking about beams, yes, we can apply uniformly distributed load. So even if you apply uniformly distributed load in a truss, that would actually be not converted to equivalent loads at the joints of the truss. So uniformly distributed loads cannot be applied in a truss member, but uniformly distributed loads can be applied in beams and frames, and even if you have the uniformly distributed load and you want to calculate deflection at a point, you don't have to convert that uniformly distributed load into a point load. You can apply a separate point load P and then calculate the deformation at that point due to the externally applied uniformly distributed load by using Castigliano's theorem. So you don't have to convert it into a point load as we have mentioned. You apply a separate point load at the point where you have to calculate the deflection and then use Castigliano's theorem. But this is applicable for uniformly distributed load cannot be applied on the truss member. It has to be applied as equivalent joint loads on the joints of the truss. Why Castigliano's method can't be used for finding temperature changes in the beams? What I meant to say is we used a virtual work method for calculating deflection of beams due to temperature changes, but Castigliano's theorem, it cannot be used for calculating a deflection due to temperature changes, because here we are directly applying the external loads as well as the load P. But if you have any temperature change, there is no way of accounting for this in terms of member forces and following Castigliano's method. So if you have temperature changes and you want to calculate deflections due to internal temperature changes in a member, the best method to use would be the virtual work method. In deflection formula, we are getting units Newton meters, but in the slide they showed as millimeters. If you are referring to the slide number 63 that I am showing now, yes, this has kilonewton square meter and this has Newton per millimeter square. So it gives you Newton millimeter as you have mentioned. But remember, on this side there is a unit load 1 Newton. So that Newton and Newton will cancel out and you will be left with millimeters on both sides. So always remember, if you look at the original formula that is being used to calculate the deflection, there is this unit load there which we have already considering. So because it is unity, sometimes we neglect it, but don't forget to consider the unit. So there is a kilonewton or a Newton on the left hand side. So if you take that into account on both sides, you will be left with millimeters. So those are all the questions I got for the virtual work method and Castigliano's theorem for trusses. So now we'll start discussing the virtual work method and Castigliano's theorem for beams. Now if you recall the calculation of internal strain energy due to bending, that is what we'll be using for calculating the deformation of beams and frames. So this is how we have to apply the virtual work method for on a beam which is subjected to some external loads. So what we do is, if we have calculated the deformation at this point A in the downward direction, we apply a unit load in that at that point in the downward direction. So it's very similar to the virtual work method for trusses. So it is in the same manner we apply a virtual load of magnitude unity at the point where the deflection has to be calculated, and then calculate the internal virtual moment at any arbitrary location x from the left support due to the virtual load using the method of section. So you apply that virtual load of magnitude unity and calculate the moment at any section x. So that is represented by this function small m. So m will keep on changing over the length of the beam and it will be a function of x. Then you apply the real loads or the external loads on that beam and you calculate the internal moment at any arbitrary location x from the due to the real load. So first of all, you calculate moment due to virtual load at any section x from the support, and then you calculate the moment capital M at any section x from the support. Now the deformation of a small element due to the moment due to the actual load is given by, if you recall, m dx over ei. So that is the deformation or d theta. So the internal strain energy due to the virtual moment and actual deformations is given by m d theta. So where theta is capital M over ei into dx. Now again, the external work done by the virtual load of magnitude unity due to the external applied load is equal to 1 times delta, where delta is the deformation at that point A due to the externally applied loads. So 1 is the virtual load and delta is the location of that point where that virtual load is applied due to the external load. So this is the external virtual work that is done after the application of the external loads. And this is the internal virtual strain energy in the beam elements due to the virtual moment and the deformation of that element due to the actually applied loads. So if you want to find the internal virtual strain energy over the entire length, you integrate that with respect to x from 0 to L. So d theta would be replaced by m over EI into dx. So you replace that here and you integrate it with respect to x from 0 to L. So that is the final formula that you will get, where 1 is the virtual load, delta is the deformation at that virtual load application point due to the external loads, and this is the internal strain, virtual strain energy due to the virtual load and the deformations due to the actual loads. Now, in the same manner, if you wanted to calculate the moment at a point, so instead of applying a virtual load, you apply a virtual moment of magnitude unity, and the rest of the steps are same. So apply the virtual couple of magnitude unity at that point A where you want to calculate the rotation. The next thing is you calculate internal virtual moment m theta at any section x from the left support, apply the real loads on the beam, calculate the internal moment m at any distance x from the support, then calculate the rotation at up that section using the formula d theta is equal to m by ex. Then again equate the external work. In this case it is the external virtual moment and the rotation at that point due to the external load. So that is the external virtual work, and the internal virtual strain energy is the given by integration 0 to L m theta d theta. So here again you replace d theta by capital M over EI dx, where capital M is the moment at any section due to the actual loads or the external loads. So here the formula would be 1 times theta into m theta m over EI into dx, where m theta is the virtual moment at section due to the unit virtual moment applied at this point where the rotation has to be calculated. Now, if you want to calculate the deflection or rotation of a beam using virtual work method, you notice that there is an integration of functions which are of two functions which are basically functions of x. Now m theta and capital M are functions of x, and they may be of different order. So what we sometimes do is we'll be using some tables which are provided to calculate these functions, which I'll show you in the next slide. But before I show you those tables, I just wanted to mention one more point. So if you have beams with concentrated load, concentrated moments, or discontinuity in distributed load, you need to consider these functions separately. So any change in the moment diagram would require you to consider separate equations, just like we did for the double integration method. For every discontinuous loading, we were considering separate. Similarly, in this method also, we'll be using separate integration limits for regions which have continuous loading. So every time there is a change in the loading, or every time there is a discontinuity in the moment diagram, we have separate equations. Now the one thing you have to remember, so the origin that you use to express the moment due to virtual load and the moment due to the external loads, they have to be same. You cannot use different origins for calculating moment due to virtual load and external load. So if you look at this beam here, it has 3 different regions where separate equations of moment will be required. So if you have to calculate this deflection at this point D, you have to apply a virtual load here. So that makes it 4 different regions. So one is between A and B, one is B and C, one is C and D, and the last one would be D and E. So if you notice that for calculating the moment due to virtual load as well as due to external load, the same coordinate systems. So for this, x1 is calculated from here. For the virtual load also, the expression of moment is calculated from here. So x1 is taken from support A. For this region, x2 is taken from support A. For same thing here for the real loads, for calculating capital M, x2 has to be taken from support A. So whatever origin you use to calculate this function capital M due to the applied loads, should that same system of origin has to be used for calculating small m due to the virtual loads. So now I can show you the standard tables that are useful for calculating deflection due to the bending action. So here there are the different types of variations that you can get in the moment function. So if it's constant, then it is like it is uniformly increasing. It can be trapezoidal, it can be triangular, it can be a reverse triangle. So here it is maximum on one side, here the maximum is on the other side. Same thing, the capital M can also have different forms. Here this is a quadratic form. So what this table gives you is the formula for this integration, M, capital M dx. So that is the formula for this. I have one function of M, one function of M dash. Then the integration over this entire length is given by this formula. So these integration formulas are very useful for calculating the deflection of beams using the virtual work method. So now we'll take an example of a simple cantilever beam which is applied to a load of 3 kilonewtons. What we have to determine here is the slope at point B, that is the midpoint of this cantilever beam. The I and E values of the beam are provided. I is 60 into 10 to the power 6 and E is 200 into 200 GPa. So now what we have to do, since we have been asked to calculate the rotation at this point B, the virtual load that has to be applied is actually a virtual moment, that is a moment of magnitude unity at this point B. So this is the actual load, which is 3 kilonewtons acting downwards, and the moment diagram of that beam under the applied load is shown here. If you apply a unit virtual moment at this point B, the moment diagram of that beam is here, where it will have a moment of -1 kilonewton meter over only half span of the beam. So now if you want to use the formula integration mm over ei dx, you see that the moment function for the beam does not have any discontinuity or remains uniform, or remains the same under the external load. But under the virtual load, or under the virtual moment in this case, the moment function has a break or a discontinuity. Over this half span it one. So we have to consider two separate integrals. One is from 0 to 5 and the other one would be from 5 to 10. Now if you look at this part, here it is angular distribution from 0 to -15, but here it is 0. So what does that tell you? That tells you if you put this small m is equal to 0, this integral will be 0. So that basically tells us you don't need to consider the integration of the moment functions over this half, because here it is 0, so it will become 0. So we have to consider it only between points B and C. Now between points B and C, due to the applied load, the moment distribution is trapezoidal, and due to the virtual load, so if you look back at that table that I showed you 2 slides back, it is one is trapezoidal distribution and the other one is uniform distribution. And if you have that integration, the formula is half m into m1 dash plus m2 dash. So these are the values of the moments at the two ends of the trapezoid, and the length L. So the length L here would be the length over which the moment function is changing. So here it is 5 meters. So we'll use that formula to calculate the value of the integral here. So that is what we are doing, 0 to 5 mm dx. So here the origin for x is at point B. So if you use that formula, it is that ei is constant, half m, this is the uniform m, which is -1 into m1 plus, so that is -15 plus -30 into the length, which is 5. So that divided by the values of E and I will give you theta is equal to 0.009375 radians. So that gives you the value of the rotation at this point. Now here again notice that on the left hand side you have kilonewton meter into theta, which is in radians. On the right hand side you have kilonewton square meter cube, kilonewton by meter square into meter fourth. So if you cancel the unit, you will see that the unit of theta is coming out to be in radians. So that is a simple example of a virtual work method for calculating the rotation in a beam. We'll have one more example where we'll calculate the displacement in a frame using the virtual work method. So we have a frame here, roller support at one end and a fixed support at this end. The moment of inertia of that frame is given and it is subjected to a uniformly varying load of 4 kilonewton per meter in the vertical member AB. Just want to rectify myself. This support is actually a pin support. It is not a support. So, and this is a roller support. So if you draw the moment diagram of the beam, this is the moment diagram of the beam under the applied loads. This is 200 kilonewton. There is a typing error. This is 200 kilonewton meter. This is also 200 kilonewton meter. These are the reactions. Now, since we have been told to calculate the horizontal displacement of point C, that is this point, so the virtual load has to be applied at. So this is the total load of 1 kilonewton applied at point C. These are the reactions due to that applied load, and these are the moment diagram. Again, these units are not correct. It should be kilonewton meter. So now you have a quadratic distribution of the moment in the vertical member due to the external loads, and a triangular of moment in the vertical member due to the horizontal loads, the virtual loads. Now, if you want to calculate the value of the integral mm into L, because of these two distributions, you have to use a triangular distribution in combination with a quadratic distribution. So the formula would be 5/12 mm dash L, where m is the peak value of the moment due to the triangular distribution, m dash is the peak moment due to the quadratic distribution, or vice versa. Does not matter in which one you assign as m and which one you assign as m dash, but this is the formula that you will be using for calculating the deformation due to the bending in the vertical member. For the horizontal member, both of them are triangular distribution, and maximum of the maximum value of those triangular distribution occurs at the same point. So you have to consider a triangular distribution with a triangular distribution having maximum on the same side. So that formula is 1/3 mm dash L. So with these two formulas, we will be able to calculate the horizontal deflection of this joint C of the frame. So for the vertical member, the length of that member is 10. So if you integrate mm over into dx, the formula would be 5/12 into 10 into 20. So into 200, I'm sorry. So this 10 is coming from this maximum value of this triangular distribution. This 200 is coming from maximum value of the moment to the quadratic distribution. And this 10 is the length of this member. If you look back at the problem, this length is 10 and this length is 8. And so considering the deformations in the bending deformations in the horizontal member, we saw in the previous slide, it was 1/3 mm dash L. So 1/3 m, this is 10, m dash is 200, and here the length is 8 meters, the length of the horizontal member, and EI remained constant, so you just put the values of EI. So if you calculate this, and now here this unit virtual load as unit kilonewtons. So if you put unit here, you'll see that unit of deformation or deflection delta at this joint in the horizontal direction would be millimeters or meters. So it comes out to be 0.034 meters. So that is the horizontal deflection. Now it is positive, that means it is in the direction in which we applied the virtual loads. It is towards the right. Now the virtual work method can consider bending deformations, it can consider axial deformations, it can consider shear deformations. So now we'll see how we can consider bending as well as axial and shear deformations to use the virtual work method to calculate the deformations. Now, when we talked about the axial deformations of a rod, you remember that the internal strain energy due to the axial load N, due to a gradually applied axial load N, is given by N square L over E. However, the virtual strain energy due to the axial load is given by N into L, capital N into L over AE. So what happened in this case? We first applied this virtual load small n, due to which it undergoes deformation delta, and then we applied an additional real load capital N, due to which it undergoes its deformation delta dash. So the work done by the internal strain energy due to the virtual load is N into NL over AE. So the deformation of this rod due to this applied load, additional applied load N, is N into L over AE, and the virtual load was already applied, so that internal strain energy due to the virtual load undergoing the deformation of the actual load is N into capital N into L over AE. Now coming to the virtual strain energy due to shear forces, if you have an element which is subjected to a shear force P, then the shear stress on that element is given by this term, tau is equal to K into V over A. Now this V is the shear force at any section of a beam. K is called a form factor, which depends on the beam cross section, and we have given you some standard values of K that you can use for typical cross sections. For rectangular cross section, you can use 1.2. For a circular cross section, you can use 10 by 9. If you have an I beam, then you can use K is equal to 1, but in that case, remember, this A is usually taken as the area of the web. So that is the shear stress. Now the shear strain of the beam is given by tau over G, where G is the shear. If you replace tau by Kv over A, so the shear strain is given by Kv over Ag. Now the shear strain is given by this deformation, this is the shear deformation, that is delta y over the length of that small element dx. So dy is given as the shear deformation delta y, that is the vertical deflection due to the shear deformation of the beam element of length dx subjected to a shear strain gamma, is given by dy into gamma dx. Now gamma is kv by ag, so you put that here, so it is kv by ag dx. So the internal strain energy in the beam due to the shear force V acting on the beam section is given by V times VAG into K into dx. So, or it is V times dy. So this small v that you see is the shear force at that beam section due to the virtual load. The internal strain energy due to the virtual load undergoing deformations due to actual shear, the actual shear deformation is Kv by Ga dx, or in other words dy. So this is the shear due to virtual load, and this is the deformation due to the actual shear, or actually due to shear due to the actual loads. So here you replace dy by this term Kv by Ga. So the deformation over the entire length of the beam due to the shear action is given by integration of this term over dx from 0 to L. So that gives you the internal strain energy due to the shear deformation. In the previous slide, we saw the internal strain energy due to the axial deformation. So now what we'll do is we'll combine internal strain energies due to the axial deformation, shear deformation, as well as bending deformation, and calculate the deflection of a given point of a frame by considering all the three deformations. So we have that same frame which is subjected to a uniformly distributed load of 4 kilonewton per meter. It has a pin joint at A and a roller joint at C. So now includes 10 energy due to axial loads and shear forces in addition to the bending deformations. Previously what we did is we calculated the deformation or the horizontal displacement at this joint C considering only the bending deformations. Now in addition to bending deformations, we'll consider the axial loads as well as, the axial deformations as well as shear deformations. So to do that, what we have to do is plotting the bending moment diagrams that we had previously. We'll plot the axial force diagram and the shear force diagram due to the applied loads as well as due to the virtual load of 1 kilonewton at this joint where the displacement has to be calculated. So this is the axial force diagram under applied load. This is the axial force diagram under the virtual load of 1 kilonewton at C. This is the shear force diagram under the applied loads. This is the shear force diagram under the virtual load. This is the bending moment diagram under the applied load. This is the bending moment diagram under the virtual load. So if you want to calculate the total deformation considering axial, shear and bending deformations, you have to use the formula where small n is the axial force, capital N is the, small n is the axial force in the member due to the virtual load, capital N is the actual force in the member due to the actual loads, L is the length of the member, and A is the cross-sectional area, E is the modulus of elasticity. Now these are the two axial force diagrams. Now again we notice that in the horizontal member under the applied load there is no axial force. So we don't have to consider the axial deformations here because in that case this capital N for this horizontal member would be 0. So that term would be 0. So we have to consider the axial deformations only in the vertical member. So under applied loads this capital N is 25. Under virtual load this small n is 1.25. So put small n is 1.25, capital N is 25, L is the length of the member which is 10, A and E are given. So this is the deflection of this joint C due to axial deformations. So this is just the first term that you see here. So now coming to the shear deformations. So these are the two shear force diagrams. This is due to the applied load, this is due to the virtual load. And this is the formula that we got for calculating deflections due to shear deformation. Now the section is rectangular, so K is taken as 1.2. Now the shear functions are V. So once again, what we can use the integration tables that we showed for the moment functions. The same things can be applied for shear functions. So this is a triangular variation. This is a uniform variation. If you recall from that table for combination of triangular and uniform variation, the formula is half into 40 into 1. So that is what we have used. Half into 40 into 1 times the length of the member, which is 10. Now in the horizontal member, both under applied loads and virtual loads, the variation of shear force is uniform. So here it will be this 25 into 1.5 into 8. So that is the deformation due to the shear, that is deformation due to shear action being considered here. K is constant for both the members, A and G are constant for both the members. So we just take them outside the bracket, and if we calculate this, this comes out to be 0.033 millimeters. So that takes into account the axial deformation and shear deformation. Previously we had calculated this deflection due to the bending deformation. So if we again look at that, it is the same calculation, 5 by 12, 10 into 200 into 10, and 1/3 200 into 10 into 8. There is a small error here, it should be 1, it is not 1.2. So if you calculate this, you will get 34.167 that we previously got. So this basically gives you a chance to compare the deflection at that joint C due to the three actions. This is one. The first one that you see is due to bending. The second one that you see is due to shear action, and the last one you got is due to the axial. So this is the overall deflection of that point C, you considering bending, shear and axial deformations of members. Now this also gives you a chance to compare the values, the relative values. You see the the deflection due to the bending deformation is much higher than these two, the shear deformation and the axial deformation. So that basically tells you that, if you remember during my first session, I said that in these beams and frames where the span is much larger than the lateral dimensions, the majority of the deflections occur due to the bending action. So this is a proof of that statement, where you can see that the order of magnitude of the bending deformation is much larger than the shear deformation and the axial deformation. So now, since we have discussed the virtual work method for calculating deflections in beams and frames, we'll move on to the Castigliano's theorems for calculating deflections of beams and frames. And similar to the Castigliano's theorem for trusses, the Castigliano's theorem for beams and frames states that the displacement or rotation of a selected point in a beam or frame is equal to the first partial derivative of the strain energy of the beam or frame with respect to a force or moment. Depending on whether you need displacement or rotation at a point, you apply force or moment at that point, acting on the beam or frame point in the direction of the displacement and rotation. So here again, you take the internal strain energies due to axial deformation, shear deformation, bending deformation, and take the partial derivative of the internal strain energy with respect to that load P that you are applying to calculate the deflection. Now here again, you see that this term is the internal strain energy due to axial deformation is Ni square Li in mod 2Ae. Now this Ni will be a function of P, because it is the axial force due to applied external loads as well as the load P combined together, applied together. Again, this Vx would also be a function of P, because it is the shear force at any section due to applied load as well as this load P that you are applying to calculate the deflection using the Castigliano's theorem. Same thing with M. M would be a function of P. None of these other terms here would be a function of P. If you take partial derivative, then again you will get 2Ni del P. And again those 2's will cancel out. Similarly here you will get Vx del P over Ag. K is also there. Same thing in the moment, those 2's will cancel out when you take the partial derivative. It will be Mx del P over Ei. Now again, as we just now saw, the displacement of beams or frame members are primarily due to the bending formations. The contribution due to axial and shear deformations may be neglected. So if you are using Castigliano's theorem, you can consider, these are the formulas given for considering shear and axial deformation, but since you know that bending is the predominant action which contributes to the deformation of these members, so you can straight away calculate the deflection using Castigliano's theorem by just considering this third term. So what we have is again that cantilever beam with a load of 3 kilonewtons at this point. Now what we will do is we'll use Castigliano's theorem to calculate the vertical deflection or displacement of point A of the beam due to bending deformation, and in the second step we'll consider bending as well as shear deformations. So the area of the beam, cross section of the beam is given. It is mentioned it is a rectangular cross section. Moment of inertia, shear modulus, and modulus of elasticity of the beams are also given. So that is the bending moment diagram due to that applied load. So now here what is happening is, instead of this, since we are told to calculate the deformation under this load itself, under externally applied load, we are replacing this load by a load which is P. And the bending moment diagram of the beam is minus PL, and moment at any section is minus PX. And if you take the first partial derivative of the moment with respect to P, it is minus X. So in order to calculate the bending deformation, you use this formula, integration from 0 to L, Mx del P over Ei. So Mx is minus Px, X is, and del Mx del P is minus X. There should have been a minus X here, so that is missing. So please consider a minus X here. So again, if you integrate that, you will get PL cube over 3EI. Now here, this is what I told you when I was discussing the Castigliano's theorem for trusses. Since we replaced that load by P here, when we are calculating the deformation, instead of taking P is equal to 0, we take P is equal to the actual value of the load that is actually existing on that beam. So we use P is equal to 3. So we put that here, put the value of the length, put the values of E and I, so you'll get the bending deformation. So that is the deflection of this point considering the bending deformation. Now, if you want to consider the shear deformation, you have to apply that load, plot the shear force diagram. So here it is minus P, the shear force will be minus P, and the first derivative of the shear force with respect to P is minus 1. So you again take this formula 1.2 Vx del P over Ag, put Vx is minus P, del Vx del P is minus 1. Again here we'll get PL over Ag, this 1.2 is coming from the term K. K for a rectangular section is 1.2, so 1.2 PL over Ag. Again here instead of putting P is equal to 0, you put P is equal to 3. L is equal to the length of the member, A and G are given. If you put those, you will get 2.18 to 10 to the power minus 4 meters. So this is the deflection of this point, the free end of the beam, of the cantilever beam, considering the shear deformation. And in the previous slide, we saw the deflection of that point due to bending deformation. So if you want to calculate the deformation due to bending as well as shear deformation, all you have to do is add these two up, 0.083 and 2.18 into 10 to the power minus 4. Again, you notice that shear deformation is of one order less than the bending deformation. So that gives you some idea about calculating the deflection of beams and frames using Castigliano's theorem. So with that, I will now like to just round up these two methods, that is the Castigliano's theorem as well as the virtual work method. So just remember that both these are energy methods, that is, they are based on the principle of conservation of energy. So they are useful for calculating deflection of structures due to axial and shear deformations in addition to bending deformations. Now this is applicable for beams and frames. For trusses, it is calculating deflection of the truss due to axial deformations only, because in truss members you don't have shear forces and bending moments. The virtual work method can be used to calculate deflections due to temperature changes and fabrication errors also, as we saw for trusses. So, but Castigliano's theorem you cannot use to calculate deflections due to temperature changes or fabrication errors. Now, this virtual work method and Castigliano's theorem can be used to obtain deformation of structures at single load points. They cannot be directly used to obtain equation of deformed structures, just like you were able to do for double integration method. You were able to obtain the deflection, the equation of the elastic curve. In this method, you have to calculate deflections at single point. You cannot obtain the equation of the deformed structure. Similarly, you cannot obtain locations of maximum slope or maximum deflection that you could do for calculating that you could do for double integration method. So those are some heights of this energy methods that I wanted to discuss before I close this topic. So that basically brings me to an end of this talk. I will now take some questions that has already been asked while I was going over these topics, and if time permits, I will quickly discuss the assignment problems that I have given on the energy methods. So I already have some questions here. First question I am getting here is, what are the applications of Castigliano's theorem? Application of Castigliano's theorem is calculating the deflections of trusses and frames by considering their axial deformation for trusses and axial shear and bending deformation for beams. Now it has a slight advantage over the virtual work method, and that is in virtual work method you have to separately find member forces in the structural components due to virtual loads and externally applied loads. But if you are using Castigliano's theorem, you can apply that load P as well as the external load simultaneously, calculate the internal moments, shear force and axial loads, which will be functions of load P, and then you can take the partial derivative. So it is, in some cases it might be a bit quicker than the, or it might be a little less elaborate than the virtual work method. Also, if you have to calculate deflections at two different points using the virtual work method, then you have to apply unit load separately at those 2 points. However, if you are using statically method, you can apply two loads P1 and P2 and then take partial derivatives with respect to P1 and P2 at those 2 points and calculate it from a single structure. Next question I got is, how can we use Castigliano's theorem in practical life? As I showed here, I have shown some examples where we have taken a cantilever beam as well as we have taken a truss. Those are actually real life problems or practical problems that you might see. So, and there basically if you go through those examples one more time, you will see how we can use the Castigliano's theorem for solving a truss problem or a frame problem. Why we don't consider gradual load application in case of virtual energy calculation? As I mentioned, I think I got this question before I started my discussion on energy methods for beams and frames. What we do in virtual work method is we consider gradual load application, but what we do is we apply the virtual load first and then we applied the external load. So even though the virtual load as well as the external load is applied gradually, you don't get that half term for calculating the work done by the virtual load or the internal strain energy due to the virtual load undergoing deformations under the actual load. So the load application is gradual, but the virtual work is first applied and then the external work is applied in the principle of virtual work. Now this is appearing like a comment than a question. It says principle of virtual work basic is a smart way. So I would consider that to be a comment rather than a question. Yes, it is a good or effective way of calculating deformations at any particular point. As I showed you, if you simply apply principle of conservation of energy, it will give you deformations only at the points where the load is applied. However, if you want to calculate deformations at any other point other than the point where load is applied, then definitely the virtual work method is a very effective way of considering that deformation. Now, since we don't have much time left, what I'll do is I will try to quickly go over the assignment problem that I gave you on virtual work method of trusses and frames. So this is an assignment problem that I gave you. Oh, I already got another question is, please explain exercise number 11 once again. Okay, so I have to go back. Okay, so this is number 11 where we calculated horizontal deflection of this joint C due to this applied load. And now here we are considering bending deformation as well as shear deformation and axial deformation. Now since we are considering, we have to calculate the horizontal displacement of this joint C, we are applying a virtual load of 1 kilonewton at that joint. We are drawing axial force diagram, shear force diagram and bending moment diagram. Also we are drawing the axial force diagram, shear force diagram, bending moment diagram due to applied loads. Now in order to calculate horizontal deflection of this joint due to the axial deformation, we consider the axial load diagrams. So first of all, if you look at these two axial load diagrams, you notice that in the horizontal member there is no axial force due to the applied loads. So that means you don't have to consider the axial deformation of the horizontal member to calculate the horizontal displacement here. You only have axial deformations of these two members, and the formula for calculating the horizontal displacement due to axial deformation is given in this slide. It is n into n times L over AE, where small n is the axial force due to virtual load, which is 1.25. Capital N is the axial force due to the applied load, which is 225. L is the length and AE. So that gives you the deformation or the displacement of this joint due to the axial deformations. For the shear deformations, we consider the shear force diagram due to the applied loads and due to the virtual loads. And again, we use this formula, which is KVV over AG dx integration over 0 to L. Here again, we are using the integration tables. So if you go back to the integration tables here, so if you go back to, so this is triangular variation and this is uniform variation. So triangular and uniform variation, the formula is half m into m dash into L, where m dash is this, I'm sorry, m dash is here, and this is m. So that is what we have used to calculate the deflection due to the shear deformation in the column, and the shear deformation in the beam is considered here. So both are uniform. So it is, if you go back, for both uniform, it is m dash into L. So here it is minus 1.25 minus 25 into 8. So and K is 1.2, A and G are here. So this is the deflection at that joint C or point C due to the shear deformation. And again, the bending deformation, you consider the bending moment diagrams due to the applied load and the virtual load, and you consider, you take this formula again, where you again consider the integration table. So that we have already done before. Only thing is there is a typing error here. This is 1. So if you calculate this, you will get 34.167, same as what we got. And then you just add the deflection of that joint due to bending, shear and axial deformation to get the overall deflection. Hopefully this has been clear after the second explanation. What are the main assumptions in Castigliano's theorem? As I said, Castigliano, if you recall, I said it is applicable for members which do not have any temperature change, no yielding supports and linearly elastic material. Those are primarily the main assumptions in Castigliano's theorem. Limitations of Castigliano's theorem. This is pretty much similar to the previous question. Castigliano's theorem cannot be used for calculating deflection in members which have temperature changes or support settlements, or if you have linear inelastic members, then you cannot use Castigliano's theorem for calculating the deformation or deflection of those members. So what this is telling is, determine the vertical displacement of joint A of the truss shown in figure 5 under the following conditions. One is under the given loading. The second one is when members AB and BC, that is these two members, experience a temperature change. And third is member AE is fabricated 5 mm too short. Now draw that truss, virtual load has to be applied here. So if you apply this virtual load, and if you are familiar with the methods of analysis of trusses and joints under special conditions, just by looking at this, you will see that this member is a zero force member, because at this joint, these two members are along a straight line. This is the third member. So similarly, at this joint, this is a zero force member. These two are along a straight line. So these two are zero force members. So you get member forces in AB, BC, AE and AD. When you draw the table, you can straight away eliminate these two members, because under virtual load this will have no member force. So in other words, n small n would 0. So all you have to consider is AB, BC, AE and ED. You don't have to worry about EB and EC. So calculate the member forces due to, in each of these four members due to this unit virtual load, as well as calculate the member forces in these four members due to the external loads that is given. You know the length of these members, and then take the summation of N and L over AE and divide. So take summation of N and L and divide that by AE. You'll get the deflection at this joint. Now, when you are having temperature changes here and here, all you have to consider is this into the temperature into alpha delta T L in this member into this small n small n in this member into alpha delta TL of that. So those two, just take the product and take the summation. That will give you the deflection of this joint due to the temperature changes in AB and AC. For calculating deflection of this joint due to the fabrication error here, the fabrication error is delta L in AE. Just multiply it with N of AE. That is the member force in this member due to this virtual load. So that will straight away give you the vertical deflection of this joint due to the fabrication error in this member AE. So those are the quick discussions on that problem. Now I'll go on to the last assignment problem that I have given. So calculate the horizontal displacement of points. Calculate the horizontal displacement of point C for the frame shown in figure 6 using principle of virtual work and Castigliano's theorem. Now, so you have that frame, and what you are told to do is calculate the horizontal displacement of this joint. Now, you see that an external load is already at this joint. So when you are solving it by virtual work method, you have to calculate the bending deformations of this frame due to this applied load as well as due to a virtual load of 1 at this joint. You have to consider them separately and then use the formula integration m by EI dx for these two members. This is the first member and this is the second member. That small m is the moment in each of these members due to this virtual load. Capital M is the moment in each of these members due to the external loads. Now, the only difference here is when you are trying to solve this by Castigliano's method, instead of applying the actual load here, you apply the load P and you apply the other external loads. You calculate the strain energy due to bending in this member into this member. That will be given by formula m square dx over EI. Now here m will be a function of P. So then you take the derivative of partial derivative with respect to P. Now again here P would be not equal to 0 but equal to 60. That is the value of the actual load that has been applied here. So again, if you work it out in detail, you will be able to see the difference between the virtual work method and the Castigliano's theorem. Okay, I got two more questions. I'll quickly take this before I close this session. What is meant by virtual work? If you know the meaning of the word virtual, that means it is not real. So here what we are doing, we are applying a load of magnitude unity which is not real. That means it is not an external load, it is just an imaginary load or unreal load, and we are considering the work done by that virtual load to undergo the deformations under the actual loads. So the work done by virtual load to undergo deformations due to the actual load is called the virtual work. What are the applications of Maxwell's reciprocal theorem? This question is more effective for calculating deformation of statically indeterminate structures or analyzing statically indeterminate structures. So Maxwell's reciprocal theorem are normally applied for analyzing statically indeterminate. So since this topic was mostly related to statically indeterminate sections, for calculating deflections of statically determinate structures, there is no direct application of Maxwell's reciprocal theorem which can be effectively used for calculating the deformations or deflections due to the effect due to the statically determinate structures. So I think the time is almost up. So I will now conclude this session. Hope you have learned something over the past sessions on how to calculate the deflection of statically determinate structures that I have explained the various methods. If you have any questions, please feel free to contact me. My email ID is lashkar@civil.iitb.ac.in. Thank you.